Hi, in this video, we want to take a look at confidence intervals. Now, I'm not going to get really into the weeds of this. I want us to dive in and look at these in a manner that is consistent with how we actually use them. Okay, so for a moment, think about estimating a value using data. First and foremost, if I'm using data, I don't know what's going on. If I knew what was going on, I wouldn't be using data, right? Okay, so that's the first thing to remember. So I want to estimate, let's say, the true population average using data where I believe that the population is normally distributed and we have a constant variance. So here I'm going to say that my variable is normal. I have an expected value of mu, and the variance is sigma squared, just a regular old normal distribution. Okay, well, I'm going to go out and I'm going to collect some data because I want to estimate this expected value. I want to know what the true average is. So I go out, I get some data. So here, this is from the sleep data set. It's in the data sets package in R, by the way. And then I take an average. I take the sample average to estimate the population average, right? Makes perfect sense. And now I get 1.5. All right, so now I've got an estimate. Now, next question is that a good estimate? At this point, I don't know. Maybe not. So I need to pull in some more information to figure out, should I go with this estimate? Is this reliable? Am I very confident that the sample average is close to the population average? I want some kind of measurement of how good this is. All right, so, and I want an idea about like how close is the sample average to the population average. Potentially, mu could be any number on the number line. So mu could be anything from negative infinity to positive infinity, anything along the number line. So when I look at this, I mean, I don't know. I don't know if 1.5 is a good estimate. All right, well, let's take a step back and let's start thinking about what we're doing in terms of the probability distribution. Okay, well, I have normal distribution, right? Normal distribution. So I know that if I take a quantile to the left and a quantile to the right on each side, if I take so let's say that my type 1 error risk tolerance is 0.05. If I take the quantile that it corresponds to half on the left, so that would be 0.025, and then I go on the right 0.975, and then I get the two quantiles, and this is simplified because of symmetry of the bell curve. So I know that this is true, that if I go like this, the probability of an observation, standard normal, being between the two quantiles is equal to 1 minus alpha. Okay, well, let's think about this for a moment. I know that x bar minus mu divided by standard error, sigma divided by square root n, that this is standard normal. Okay, well, that's standard normal. So it's okay for me to substitute z with this. Now, that's something that's very interesting about this whole probability situation, is that inside the probability, inside this p thing, I can do any correct mathematics on the inside of the parentheses, all I want, and everything remains correct. Okay, so let's do that. Let's go through. So here I've got a fraction. I know that we hate fractions, but I've got to deal with it right now. Here's a fraction. So let's go ahead and, move some things around. Let's say I go through, I multiply everything by the denominator, right? That will get rid of my fraction. So I multiply this by sigma over square root n. I multiply this by sigma over square root n. You see that I have that and that here. Now, what I'll be left with is x bar minus mu. So now let's go ahead and subtract x bar from everything. So I see that negative x bar minus z times standard error, negative x bar plus z times the standard error. Well, I know, because of the mathematical properties of what I'm doing, is that the probability that this interval contains negative population average is 1 minus alpha. Okay, well, let's keep on working with this. All right, so I see I have a negative sign there. Now, does it make sense to have negative sign on the mu? Well, not really. So, I mean, it's just kind of cumbersome. It's not that hard to interpret, but there's no reason to keep it. So let's go ahead and multiply everything by negative sign. All right, so when I multiply this by negative, that becomes positive, that becomes positive. So here, we're looking good. Now remember, when I multiply across inequalities by negative sign, they flip. So this becomes like that. And when I multiply over here, that becomes positive, this becomes negative. Boom, we got that. And remember, multiplying it across inequalities flips the direction. And now what I do, just to make things a little bit easier, I like to keep things going from left to right on my inequalities. I like to have the alligator opening up to the right. Alligator is the big one, right? Remember from elementary school? So here, this, I'm just moving it to the far left. I'm moving this to the far right. And I'm switching the inequalities. And you'll notice that this part is the same as this part. Okay, so we can see that the probability that the interval defined by this and that, the probability of that interval containing the true population average is equal to 1 minus alpha, 1 minus our type 1 error risk tolerance. Okay, so now that is before I collect data. Before I collect data, I know that I have this probability that this interval will contain the true population average. Okay, well, that looks interesting. Let's go ahead and proceed with that. Now, something about this is this setup, this probability statement, only applies before we collect data. Okay, now why is that? After I collect data, either mu is in that interval or it's not. There's nothing random. Once I have fixed hard values coming out from my data, it's no longer random. It's a true or false situation. It is or it isn't. Okay, so here, before I collect the data, I'm dealing with the probability that the parameter value is inside the interval. After I get the data, it is or it isn't. So I can no longer use the word probability because there is no randomness. Okay, so what wording do we use? We use confidence. And this is where the term confidence interval comes from. And it's an interval and it reflects our confidence on what's going on. So we say that we are 95% confident that the population mean is inside our interval. So this is very particular wording. It's important to follow this exact wording because it's not random at all. Once you put the number down on paper, once you have the data, it's no longer random. It's a fixed thing. Okay, so we say I am 95% confident that the population mean is inside my interval. And now the 95% comes from 1 minus alpha. If I put alpha equal to 0.05, then the probability that, before collecting data, the probability of the interval containing the population average is 1 minus alpha, which corresponds to 95%. All right, so this 95% comes from 1 minus alpha. That's where we got that. All right, well, let's think about the interval for a moment. So this gives me a range of realistic values. So one use of this, let's say my point estimate is 2.1, and I see the number 2 is inside my interval. Well, if I'm going to be talking to people, I'm not going to say 2.1, I'll just say 2. I can pick a number that's easier for communication, that is relatively that's close to my point estimates, and it's inside my confidence interval. It's okay to do that. So this is something that can improve our ability to communicate and also make it, we're picking numbers that's easier for us to interpret and work through. Instead of having 2.386291, we're just say 2, because 2 is inside that confidence interval. All right, well, let's think about it a little bit more. If I had a really, really good estimate, then I would have a lot of precision. If I have a lot of precision, then my standard error is very, very small. Well, if I look at this, here is my standard error. Here is my standard error. If standard error was super, super small, like really, really close to 0, then I can see that this part is going to be very close to X bar. This part is going to be very close to X bar, and there isn't going to be much width in that interval. Well, okay, so how we interpret this, when I see output from R or SAS or SPSS, it gives me an interval. If I see that the interval is narrow, I have more precision. I have more, I have more precision, and I feel more confident about my point estimate. Now, if it's super wide, I go, that's a very wide interval. I don't have much precision. My point estimate may be a good estimate, it may be a bad estimate. I don't know. Okay, so one of the reasons why these confidence intervals are so important is that by looking at the width, I can check to see, is this worth using, yes or no? So wide intervals indicate less precision in our point estimate. Narrow intervals indicate greater precision in our estimates. But wait, there's more. We can actually do hypothesis testing with confidence intervals. Okay, so what's going to happen? If I'm going to do two-sided hypothesis test, remember two-sided hypothesis test, the null is an equal sign, the alternative is not equal. Okay, so any value for a hypothesis test so any value inside that's part of the null, that it's equal to this particular value. If that value is inside the interval, we fail to reject the null hypothesis. And any value that's outside the interval, we would reject the null hypothesis in favor of the alternative, where we conclude they're not equal to each other. Okay, so if I have a hypothesized value, I'm doing two-sided hypothesis tests, and I see that the value is inside the confidence interval, I fail to reject the null hypothesis. Inside the confidence interval, fail to reject. Outside of the confidence interval, I reject the null hypothesis in favor of the alternative, okay, in favor of inequality. All right, so now let's look to see how we do this in R. All right, so let's do a confidence interval for a normal random variable. So I'm going to take the sleep data set. I'm going to use the extra data, and I'm going to run t.test. So I'm going to run a t-test in R, and when I do this, it will automatically spit out a confidence interval. Okay, so if I was doing hypothesis tests and my null hypothesis had any value in this interval, I automatically fail to reject the null hypothesis. Okay, now here I can see that 1.5 is the middle of the interval. That's my point estimate. And it's saying that 0.6 to 2.5 are realistic values to be used as point estimates. Okay, so 1.5 is in the middle. Depending on what I'm doing, that might be enough precision, that might not be. If it's not enough precision, I need to go get more data, more than likely. And you'll notice that 0 is outside the confidence interval. So, and my p-value is very, very small, because the default setting is to test to see if the true mean is not equal to 0. So here's my alternative hypothesis that's automatically being conducted. So here, the alternative hypothesis of not equal to 0, I see 0 is outside of the interval. I reject the null hypothesis and conclude that the true mean is not equal to 0. Okay. Now let's do confidence intervals for proportions with binomial data. All right, so when I'm using binomial data, I have two options with this. I have prop.test and I have binom.test. Okay, prop.test uses the central limit theorem to approximate the binomial distribution, and the binom.test uses the exact distribution. So in most cases, we want to use the binom.test because it's more precise. The exception to this is whenever I'm presenting to an audience that likes using the central limit theorem to work out these details. This is common among academic journals that a lot of scientists or social scientists don't actually realize that the computer can actually give us a more precise value, more precise evaluation. And normally when it comes to journals, when I'm writing a research paper, I'm going to do what other people have done in that journal, because by being consistent with other people, I'm more likely to get past the editor filters. And so if I see that the people who have written recent papers use the proportional test using the central limit theorem, I'm going to do the exact same thing because I want my paper published. Remember, our goal when we do statistics is to convince someone of something, even though it's only approximation. It's not as good as binom.test. It's the way I'm going to go because I need my audience to buy in on my work. Okay, so let's go ahead and let's run through an example. Here I'm going to do a larger sample size. All right, so I go ahead and grab a data point. So let's say that I flipped a coin 100 times, 56 of them came up heads. Okay, that's what I'm generating here with this R binom. I want to see from a hypothesis point of view and a confidence interval point of view, what are realistic, proportion of heads. All right, so I'm going to use prop.test. Here I've got 100 trials. I'm doing the two-sided alternative hypothesis test. And so here, on the default is going to be 50-50, by the way, on this. I could put in a different P if I wanted to. So when I work through this, here's my confidence interval. So any value that's inside that interval, if I was to do a hypothesis test with that value, it would automatically be failed to reject the null hypothesis. For anything inside there, anything outside would be reject the null hypothesis in favor of the alternative, which is inequality. Okay, so here we're testing for this, or the true P is not equal to 0.5. Here I failed to reject the null hypothesis, and here's my sample estimate. All right, that seems reasonable. 0.5 seems like it's pretty square into that range. Okay, so now that's with the that is approximating the distribution using the central limit theorem. Let's do it again with the exact distribution. All right, I get 0.46 and 0.66, and I get the same p-value. So when I have larger data sets, when I have more observations, prop.test and binom.test give me practically the same thing. There is a difference. There's a very small difference, but practically speaking, there's not much of a difference. Now, when I get smaller sample size, this is where we see problems. All right, so here, my sample size is 10. It's only 10. And I want to run the confidence interval on the proportions of heads. Okay, so I just use prop.test. I say n is equal to 10. I'm doing a two-sided test. And I can see my confidence interval is 0.27 to 0.86. All right, I mean, it seems reasonable, all right? Now let's go down here. I get, when I use the binom test, I get 0.26 and 0.88, slightly different. Okay, so this is a little bit wider than prop.test. All right, this is the one that I would personally use. I would use the binom.test if I had that option. Now, so whenever I have a large sample size, it's going to be so close, I really don't care about the difference. But when I have a smaller sample size, it's a difference. My advice to you, if you don't have a problem with what your audience wants, use binom.test. If your audience wants you to use the central limit theorem approximation, use prop.test. All right, so now let's go ahead and recap. First, confidence intervals give us an interval of realistic estimates of a parameter. Okay, that's true for any type of confidence intervals. Remember, confidence intervals can be applied to any time that we have something estimating as a parameter. All right, so by using an interval, I'm getting more information than I would from a single data point. So confidence intervals are taking advantage of our data, the distribution, and our type 1 error risk tolerance, alpha. Okay, so what's going on is that using the distribution and our error risk tolerance, we get our quantiles. Okay, and then we use our quantiles and our standard error measurement and our statistic estimate to get an interval. Narrow intervals means we have more precision in our point estimate. Wider intervals mean we have less precision in our estimates. And when I do two-sided hypothesis testing, any null hypothesis test value inside the interval gives me fail to reject the null hypothesis. Any null hypothesis test with a value outside the interval, we will lead to reject the null hypothesis. All right. All right, well, that's all I've got for you. Take care and goodbye.